Okay, so this is a review problem. This is not in your notes, so you can either write it down somewhere or just watch and listen, whatever you want to do. Just kind of a little bit of a review here. Let's say we have a 5-card hand, and we want to know the probability of exactly 2 diamonds. Okay? So we want to find the probability of exactly 2 diamonds. Now, first of all, it's a probability question. Probability questions are always going to be fractions. Does anybody want to take a guess, or do you know? What is the denominator, the bottom of this fraction?
52C5.
Yes, 52 cards, choosing 5. The total goes in the bottom. That is going to be the denominator for every card problem that you are choosing 5 cards. If for some reason you wanted a 6-card hand, it would be 52C6. That's the denominator, because the denominator is the total. Great job. All right, now, up on top, we want 2 diamonds. What's that going to look like? 2 diamonds. How many diamonds in the deck, guys?
13C2.
Yep, so we're going to start with 13C2. That's the beginning, because your hand must have 2 diamonds. So there are 13 diamonds here in the pile, and you're going to pick out 2 of them. This isn't the end of the problem, though, guys, because how many cards have you chosen so far? Just 2. And how many do you need to choose? 5. So you have to pick 3 more cards. Where are those other 3 going to come from?
50C3.
That is a great guess, but it's not quite right. Because if we want exactly 2 diamonds, then what does that mean about the other 3 cards?
They're not going to be diamonds.
They're not going to be diamonds. Very good. And if they're not diamonds, how many choices do I have for them?
39.
Yep. So does everybody understand that in this problem, you are picking 2 diamonds and 3 not diamonds? And the not diamonds would be spades, clubs, or hearts. There's 13 of each, so that's 39 possibilities, and you're going to pick 3 of them. All right, if you have your calculator handy, let's go ahead and type this in. Make sure everybody remembers how. If you don't have your calculator handy, shame on you. I got 0.2743. I'm just randomly rounding that off. Anybody match that? Okay, can someone nod or give me a thumbs up or something if that's what you got? Okay, good. Want to make sure I typed it in right. All right, let's do one more like that, but a little bit different. Okay, so let's suppose that we have a group of 10 seniors and 7 juniors, and I am going to pick a committee of 4, and I want to find the probability of exactly 3 seniors. Now, I hope you see that this is very much like a card problem. In a card problem, you have hearts and diamonds and spades and all that. In this problem, I just have two categories. I have juniors and I have seniors. Now, it is a probability question. So I will have a fraction. Probability is always a fraction. And in the denominator will be the total. So remember in the last problem, our total was 52C5. What's our total this time? Anybody want to take a stab at it?
17C3 or 4.
17C4, that is exactly right. Now, let's all make sure we're clear on that. The denominator is the total. How many total people are there in the problem? 17. How many total people am I picking? 4. So the denominator is 17C4. Now, the numerator is what I want, which is exactly 3 seniors. Anybody want to take a stab at that?
10C3.
10C3 is a perfect start. That's only a start though. What's missing? It's a great start, perfect. But there's something missing. What's missing?
We need 4 instead of 3.
I need 4 total. So 3 of them are seniors. What's the other one?
7C1.
Exactly. The other one is a junior, 7C1. That is perfect. Do you see the similarity between that problem and a card problem? They're exactly the same sort of thing. And in both of these examples that I've done, you had to be careful to remember the extra pick. So when we wanted 2 diamonds, we had to remember there were still 3 other cards. When we wanted 3 seniors, we had to remember there's still 1 other kid to pick. All right, everybody okay with that? Okay, one more review problem, then we'll get started on our Venn diagrams. Let's consider the expansion 3x minus y to the 7th, and let's say we want to find the 4th term. Now, every term of the expansion is going to have 3 parts to it. It's going to have a coefficient. This one's going to have a 3x and a negative y. So there's going to be a number, and that number can come from Pascal's triangle if that's where you want to get it. It's going to have a 3x and a negative y. Now, personally, I do not have the 7th row, and that's the row we would go to in Pascal's triangle. I do not have that memorized. So I can either build my triangle over here to the side, and I have to go all the way down to the 7th, or I can remember that the numbers in the 7th row of the triangle are 7C7, 7C6, 7C5, 7C4, 7C3, 7C2, 7C1, and 7C0. Those are the actual numbers in the 7th row. So let me say this again. If you like Pascal's triangle and you are comfortable building it, you may build it all the way down to the 7th row and then just pick the 4th number over. So 1, 2, 3, 4, the 4th number over. If you don't want to build it because you don't have time or space or energy or don't know how or whatever, you need to remember that the numbers in that row are the combination numbers starting with 7. So 7C7, 7C6, and so on, all the way down. The last one is 7C0. Now, there's no need to evaluate all these. I only want the fourth one. So 1, 2, 3, 4. This is the one I want. So this coefficient is 7C4. Now, I want to remind you, I am getting this by counting. Okay? The fourth term has nothing to do with that 4. That was just coincidence. The third term would be 7C5. Okay? So please just count down. There's no shortcut, just count down to make sure you're getting the right term. Now I need to put my exponents on these, the 3x and the negative y. So again, it's a matter of counting. In the first term, the power on the 3x would be 7. So in the first term, this would be 7. Here it would be 6, 5, 4. So the power on that 3x is 4 by counting down. Then, once I know that's a 4, this has to be a 3 because these got to add up to 7. Okay, we've done this. This should be ringing bells for you somewhere along the lines. What's left to do then? We're almost done. What's the only thing left to do? Oh my gosh, people, we got to simplify it. So I got to figure out what 7C4 is. I'll let my calculator do that. So that's 35. And then I have to raise this whole thing to the fourth power. So that's going to be 81. And then I have to raise this whole thing to the third. So that's going to be negative y cubed. Now, this is a multiply. That is not a subtraction. This is a multiply. So 35 times 81 times negative 1. So negative 2835, x to the fourth, y to the third. That would be my final answer. All right, does anybody have a question about that before I erase it and we move on to our Venn diagrams? Okay, well, we're going to continue our study of probability then. We have already talked about two kinds of probability. Remember our table with all the M&Ms in it? That was one kind of probability. Our card problems are another kind of probability. And now we're going to look at Venn diagrams and probability. So the first, this is number 3. On page 60, number 3 right at the top, says consider this Venn diagram. So we have overlapping circles, and this circle represents M&Ms, and this one represents Twix. And the 30 up here represents all the people in the problem. So this tells me that there are 30 people in this box. And we apparently have surveyed them, and 11 are here, and 6 are here, and 9 are here. So we have surveyed them and gathered this data. Now, does everybody understand what the numbers in these various spots mean? What does the 6 represent?
They both like it.
They like both, that's right. So in other words, if you were all sitting out here and I said, raise your hand if you like M&Ms, and then I said, okay, now raise your hand if you like Twix, these 6 people raised their hands both times. Now, these guys over here, they only like M&Ms. They don't like Twix. And similarly, these guys like only Twix, not M&Ms. Okay, so let's answer the questions. How many students like M&Ms?
17.
Beautiful. Because there's 17 people in that box, or in that circle. There's 17 people in the M&M circle. If you are in the M&M circle, you like M&Ms. I don't care what else you like M&Ms. How many like only M&Ms?
11.
Yep. How many like M&Ms and Twix?
20.
Okay, now we gotta be careful because when we say they like M&Ms and Twix, that means they like both. It's not M&Ms or Twix.
26.
Just 6.
Yeah, just 6. When we say M&Ms and Twix, we mean they raise their hands both times. They raise their hands both times. Now the next question says M&Ms or Twix. Now that means they raise their hands at least once. They like some kind of candy. That is 26. There are 26 people that like M&Ms, or they like Twix, or they like both. Or means they raised their hand. Or means they're inside the circles. And, this was an and question. And means they're in the overlap. Or means they're inside the circles. Now, E is a little bit more specific. They like only M&Ms or only Twix. How many of those are there?
20.
Yes, indeed. Because these 11 like only M&Ms, these 9 like only Twix. So altogether, there's 20 people that only like one kind of candy. Now, F is kind of the tricky one. How many don't like any candy? Or any of these candies? How many?
4.
How did you get that? You're exactly right.
Because there's 30 people in all, and 4 haven't answered it.
Exactly. There are 30 people inside that box. These guys all raise their hands. But that's only 26 hands. So there must be 4 people out there who never raised their hand. Very, very good. Okay? All right, let's look at the next one. Each of the 28 students in the class, and you got to fill in your own numbers this time. Each of the 28 students likes jazz, country, or both. Here's jazz, country, there's 28 students altogether. All right, draw a Venn diagram showing the following. How many students like only jazz? All right, so the question is only jazz. And we know that we have 18 students who like jazz and 14 students who like country. All right, this is a little tricky. Anybody have an idea? Well, let's think about it in terms of you sitting in the room and me asking you the question. So you're all sitting here, there's 28 of you, and everybody likes something, okay? So everybody's gonna raise his hand at some point. So I say to you, how many of you like jazz? And 18 hands go up in the air. All right, put your hands down. How many of you like country? 14 hands go up in the air. Now, how many hands went up altogether?
32.
Okay, wait a minute, that's a problem. Because how many kids are in the class?
28.
Okay, so what does that mean? If 32 hands went up, but there's only 28 kids in the class, what happened? Gabe's going like this. What's he doing this for?
4 repeated.
Exactly. 4 raised their hands twice. So right here in that middle ball, right there in that overlapping area, there have to be 4 kids. Because there were 28 total, but 32 raised their hands. That means there had to be 4 overlap. Now, I know that the whole J ball, this entire ball, has to add up to 18. So if the whole thing is 18, but 4 of them are already in here, wouldn't this be 14? And then if the whole C ball is 14, but 4 of them are already there, isn't this 10? Now add these numbers up, kids. What did these 3 numbers add up to? 28, which is exactly what they're supposed to add up to. We were told in this problem that everybody raised his hand. So there's nobody out here. There's nobody out here. Everybody likes one or the other or both. Does anyone have a question about that? All right, now we're going to do more Venn diagram problems, but now we're using probability and some strange notation. So we'll need to figure out what all this strange notation means. All right, so I got my Venn diagram. And this time I have A and B. And this time I am told that the probability of A is 0.6, the probability of B is 0.5, and the probability of A and B is 0.2. So let's talk about that again. Make sure you understand. When we put the P out here like that, it looks like function notation, that's probability. So that's saying the probability of A is 0.6, the probability of B is 0.5, and this means and. So the probability of A and B. So that indicates overlap. Okay? Now, that's where you should start then, because if they're telling you that the probability of A and B is 0.2, then that means that this right here is 0.2. That's the overlap area. This symbol, the intersection symbol, that means intersection, that's where they overlap. So they overlap right there in the middle, that football, that's 0.2. Now, the whole A circle has a probability of 0.6. So that's this whole thing is 0.6. So what's just this part right here?
0.4.
Bingo. Perfect. Because the whole thing has to add up to 0.6, but you've already got 0.2 here in the middle. And then likewise out here, that whole B ball is 0.5, but you've already got 0.2 there, so this must be 0.3. Does that make sense to everyone? Now, in any probability situation, what do all the probabilities have to add up to? The total probability in any case is what? Okay, if I tell you the probability, exactly 100, perfect. Or in terms of decimals, it would be 1. They have to add up to 1 or 100%. So what do these probabilities add up to so far? 0.4, 0.2, 0.3, that adds up to what?
9.
0.9, which means that out here, we have a 0.1. So to give this a little bit of context, let's let A be apples and B be bananas. 40% of the people like only apples. 30% of the people like only bananas. 20% of the people like both. And 10% of the people don't like either one. That's what that Venn diagram means. All right, now we're going to answer some questions. Remember that this symbol right here, the upside down U, stands for and. We say and. So question B says, what's the probability of A and not B? This means not B. When you put that little mark on it, that means not B. So what this is asking me is, okay, what's the probability that somebody likes apples and they don't like bananas? So look at your Venn diagram. We like apples and we don't like bananas. What would that probability be? Where are those people?
0.6.
Be careful. 0.6 is everybody that likes apples. And we don't want everybody who likes apples. We want the ones who like apples and not bananas.
0.5.
Right here, guys. Right here. See these guys right here? Do they like apples? Yep. Are they in just the apple ball? Yep. These are the people that like apples and they don't like bananas. When you said 0.6, that is everybody who likes apples, including these, but these guys also like bananas. So this means I'm in the A ball and not in the B ball. I'm in A and I'm not in B. Well, that's this right here. These are the people that are in A but not in B. Now C is sort of similar. It says I'm not in A and I'm in B. So this is not A and B. So I am in B, but I am not in A. What's the probability of that? What's the number that represents being in B, but not in A?
3.
0.3. Yep, remember, those are percentages, so they're decimals or fractions. So 0.3. These people right here are in the B ball, but they aren't in the A ball. What does the last one in this problem say? What is this talking about? What's that saying to me? The probability of what?
0.1 on the outside.
This is you're not A and you're not B. So in other words, you're not in a ball. And the answer to that is indeed 0.1. That's exactly right. This says you don't like apples and you don't like bananas. Well, if you don't like anything, you're right here. You're that guy out there. All right. Well, you're not saying much, so I'm not sure where we're at in this. Let's try the next one to see if we can make sense of it. Farrell, you want to turn your camera on for me? Okay, so here we go. This time we have C and D. All right, so we have cookies and donuts this time. So the probability that somebody likes cookies is 75%. The probability they like donuts is 0.4. And the probability they like cookies and donuts is 0.35. Now, take a second and see if you can fill in your Venn diagram. See if you can put the numbers in the right spots, get the right numbers for that Venn diagram. Okay. Anybody think you got them filled in? Anybody feeling pretty confident?
Yeah, the 0.75 goes where the C is.
Right here?
Yeah.
Okay.
The 0.4 goes where the D is. Make
Okay.
the very right. And
Okay.
then the 0.35 goes in the middle.
Okay. Now, that makes absolute sense to me. I mean, I understand what you're doing there, but we have a humongous problem. Can anybody tell me what the problem is with those probabilities?
When you add them together?
Oh yeah, they're way more than one. So there's no way that those can be correct, because in a probability problem, we have to add up to one. Ultimately, we have to add up to one, never more than one. So does anybody have any ideas on how we might fix some of this?
Subtract either of those extremities with 0.35.
So the 0.35 is exactly right. We're not changing that. That is exactly right. So good job with that one. What this 0.75 represents, though, kids, is the entire C ball. This doesn't say just C. This is the entire C ball. So if the entire C ball is 0.75, but 0.35 is already marked, this has to be 0.40, so that the whole thing adds up to 0.75. And likewise, if the whole D ball is 0.40, but we have 0.35 already in, this has to be 0.05. David, does that make sense to you now that we talked about it?
Yeah.
Okay, good. We always want to start by filling in our overlap. Fill in your overlap first. So that was the 0.35. And then you can do subtraction to get the other ones. Now, have we accounted for everybody, or are there people out there who do not like donuts or cookies?
20%.
Yep, there's 20% out here. Who can explain, who besides Gabe can explain where that 20% came from, or that 0.20? Where'd that come from?
You add up all those and got 0.8, so it was just so right.
Exactly. In the balls, we have only accounted for 80%, 0.8. Add all those numbers up and you only get 0.8. That means there's another 20% out there who aren't in the circles. All right, so now we're going to answer some questions like we did last time. I think those B's are supposed to be D's. Sorry about that. So change all the B's to D's. Doesn't make sense. Oh, but here I am writing B's. Okay. All right, let's look at the first question. Question B. What is the probability of C but not D? So look at your picture. What represents being in C but not in D? Yeah, isn't this right here, guys, look at the picture. Isn't this red part Aren't those the C's who aren't also in D? So that is 0.4. Then that one says, let's find all of the D's who aren't in C. So you are not in C, but you are in D. You like donuts and you do not like cookies. You only like donuts. These are the only donut people. So that would be 0.05. And what does that mean?
What's
Yeah, that's not C and not D. So if you do not like cookies and you do not like donuts, then you are not in these circles, because these are the people that like cookies and donuts. You're out here. And so if the question said, what's the probability of picking a kid who doesn't like donuts or cookies, you would say 20%. These are probabilities of liking donuts or not liking cookies or whatever. Anybody have a question about that? Okay, then let's go to the next page. And this is our last kind of probability we're going to talk about. It is called conditional probability. And I would suggest that you use a tree diagram. And here's what I mean by a tree diagram. Let's read the problem first. It's number 7. If it rains tomorrow, the probability that Joe will do his homework is 40%. If it doesn't rain, the probability of his doing homework is 10%. Given that the probability of rain tomorrow is 30%, find Joe's probability of doing homework. Now, I want you to think about this problem. Aren't there are 2 things going on in this problem? Would you agree it's going to rain or not rain? He's going to do his homework or not do his homework. Those are the 2 things that are happening. Which one do you think comes first? Should we think about the rain or should we think about the homework? Which one kind of depends on the other one?
I think we should think about the rain first.
I think you're exactly right, Gabe, because whether or not he does his homework depends on the rain. In general, kids, when you read that question, the question, find Joe's probability of doing homework, that is going to be the second piece of the problem. So the first piece of the problem is going to be rain, and the second piece is going to be homework. Whatever the question involves is the second piece of the problem. So since the question is homework, we're going to make that second, and we're going to do rain first. All right? So here's how it works. Every day, it can either rain or not rain. What is the probability that it will rain? Now, I'm not talking about homework here. I'm talking about just rain. So what's the probability that it will rain?
30%.
30%. So I'm going to put 0.30. If there's a 30% chance that it will rain, what is the probability that it won't rain?
27.
Yep. because probabilities have to add up to 1. And in this case, you have two choices. It's going to rain or it's not going to rain. So 0.3 and 0.7, there's your 100%. Now, Joe's got to either do his homework or not do his homework. And that's every day. Whether it rains or not, he has to choose to do his homework or not do his homework. Now here's where you really have to be careful and read carefully. If it rains tomorrow, the probability that Joe will do his homework is 40%. So this is the branch for rain, and he's going to do his homework on this branch 40% of the time. Now, is there anyone that's got a question about why I put the 40 here? Well, if that's 40, what's this?
$60.
Yep. Kids, it's raining outside. Joe's going to do his homework 40% of the time, which means he's not going to do his homework 60% of the time. These have to add up to 1. This is it. These are the only two choices. We're going to do it or we're not going to do it. Now, if it doesn't rain, the probability of his doing homework is 10%. So this is the doesn't rain branch. Here's the homework, no rain and homework, and that's 10%, according to the problem, which means this is what? 90%. So in other words, if it doesn't rain, there's a 90% chance that he's not going to do his homework, because there was a 10% chance that he would. Does anybody have a question about any of those numbers, why those numbers are in that spot? Because now we're going to answer the question. All right, so the question is, find Joe's probability of doing homework. Now, there are actually two branches where he can do homework. He can do homework on this branch, and he can do homework on this branch. Would everybody agree that those are two branches that he could do homework on a rainy day or a not rainy day? On the branch, you're going to multiply the probabilities because it is raining and he's doing homework. So the probability of this branch is 0.30 times 0.40 or 0.12. So take your calculator out and you're going to multiply this branch, because anytime we do an and, we're multiplying. So it's raining and he's doing homework, 0.12. Now what's this one? This one is, it's not raining and he's doing homework. So we're going to multiply these together, and that will be, what is that? 0.07? Now, Joe can do homework on a rainy day, or he can do homework on a not rainy day. So if his probability of doing it in the rain is 0.12, and his probability of doing it in the not rain is 0.07, what is the total probability of Joe doing his homework?
0.19.
Bingo. Bingo. Remember that when we are doing rain and homework, we're going to multiply. anytime we are anding, we're going to multiply. Anytime we're saying, well, he can do it this way or he can do it this way, then we're adding. So we're always going to multiply on the branch. When you build your tree, you're always going to multiply each individual branch. And then, depending on the problem, sometimes you only want one branch, you don't need more. But if you have multiple branches, you will add those up. You'll add those up. So this is the final answer to the problem. All right, let's try the next one. So we have two things going on. One depends on the other. We're serving noodles and salad. And when you build your tree, you have to be very careful that you are getting them in the right order. So were you listening when I said that the question, the actual question, is always the second thing? So this says, find the probability they will serve salad. Okay, that's second. So first must be noodles. So we have noodles or we have not noodles. And then from that, we're going to have salad and we're going to have not salad. So when you got two things going on, some of you can figure it out just by reading the question, which has to come first. But if you can't quite figure it out, remember that the actual question is going to be the second thing. So since the actual question is about salad, that's going to come second. All right, so now let's fill in our probabilities. Start with noodles and no noodles. What do you think? What's your noodle probability? It's worded a little differently, but you can figure it out. How many days in a school week? Guys, how many days do we come to school in a week? 5, right? So the probability, it says they serve noodles once each school week. So what does that mean? 1 out of 5? Or 20%? That's 20%. So there's a 20% chance they're going to serve noodles. Which means, what's this one? They're not serving noodles. What would that one be? Yep, thank you. So we got a 20% chance, 1 day out of 5, 1/5, 20%. Then there's an 80% chance that we won't have noodles. All right. Now, if they serve noodles, so if you're serving noodles, there's an 80% chance that you're going to have salad. It says that right in the problem. If we have noodles, there's an 80% chance we're going to have salad. If we don't serve noodles, there's a 50% chance we'll have salad. Those come straight out of the problem. I'm not making those up. Now, what goes here? If there's an 80 on this branch, what's got to be on this branch?
20.
And if there's a 50 on this branch, what's got to be on this one? Another 50? Now, I want the probability that they're going to serve salad. So again, that's going to be this branch, noodles and salad, or it's going to be this branch, which is no noodles and salad. There's two ways we can have salad. We can have it with noodles or we can have it without noodles. So what that tell you to do with these numbers right here, always on a branch, what are you going to do? Multiply. So you're going to take out your calculator or do it in your head and you're going to multiply 0.2 times 0.8 and you're going to get 0.16, I think. And then you're going to come over here. This is the other branch you want. You want to end in salad. So 0.8 times 0.5, so 0.4. And then what are we going to do with those two? Add them. Because we could have salad with noodles or we could have salad without noodles. So the answer to that problem is 0.56. Does anyone have a question about where one of those numbers came from? All right, why don't you try setting up the number 9, the last one. See if you can build a tree diagram. Does anybody know what came first? What do I put on the first level here?
Soccer.
Yep, so soccer or no soccer. So the kid's either going to play soccer or he's not. And then he's either going to do lacrosse or no lacrosse. All right. Now, did you fill in some numbers? I put a 0.7 here and a 0.3 here. How does that look to everybody? It says the probability that a kid plays lacrosse is, or excuse me, plays soccer is 70%. And then that he doesn't play soccer would be 30%. If a student plays lacrosse, or excuse me, if a student plays soccer, his probability of lacrosse is 0.62, which would mean this is 0.38 because these have to add up to 1. And if he doesn't play soccer, it's 48 and 52 because these have to add up to 1 also. Each of these has to add up to 1. So this adds up to 1, this adds up to 1, and this adds up to 1. Now we want to know the probability of him playing lacrosse. So that's there or here. So this is 0.434. Remember, we multiply on the branch. So 0.7 times 0.62 or 0.3 times 0.48. And then we're going to add those two together, and I got 0.578. Did anybody get that answer before me? Does anybody have a question about where I got any of those numbers? Okay, well, thank goodness you have your practice tests. We'll start those tomorrow, or next time I see you. Wednesday, I guess. We'll start those Wednesday. All right, anybody have any questions? Your 9.3 second half homework will be due on Wednesday, because we just finished it, so you can maybe got a few minutes, you can work through some of that, or we can work on office hours on Wednesday if you prefer. Okay? Have a great day, everybody. Bye-bye. Bye-bye.